Hello, welcome to InfoFire, the fireside chat series from Information Matters. Each episode is a conversation between our guest and a host on a chosen topic. InfoFire brings visionaries and experts who share their perspectives and stories on a topic that shapes and impacts our information environment. I'm Shalini R, your host for this series. I have had the privilege of interacting with scholars across disciplines and around the world on a variety of topics over the last 4 decades of my career. Believing in the power of interdisciplinarity, I founded the first information school in India called the International School of Information Management at the University of Mysore, India, with a seed grant from the Ford Foundation in the year 2005. In today's episode, I'm in conversation with Gautam Menon on the topic of doing interdisciplinary science. Let me briefly introduce today's guest, Professor Gautam Menon. Gautam Menon is Dean Research and Professor of Physics and Biology and also heads the Center for Climate Change and Sustainability at Ashoka University near Delhi. He is a professor with the Theoretical Physics and Computational Biology groups at the Institute of Mathematical Sciences, Chennai, where he was the founding dean of the Computational Biology group. He is adjunct professor at the Tata Institute of Fundamental Research, Mumbai. He joined Institute of Mathematical Sciences in the year 2003, following postdoctoral research and teaching at the Tata Institute of Fundamental Research in Mumbai and Simon Fraser University in Vancouver, Canada. He was a visiting professor at the Mechanobiology Institute and the Department of Biological Sciences at the National University of Singapore during 2011 and 13. He serves on the scientific review committees of several international and national agencies, including the Human Frontier Science Program and the Wellcome Trust DBT India Alliance, as well as on a number of national committees. He was awarded a DST, that is Department of Science and Technology, Government of India Fast Track Fellowship for Young Scientists in the year 2002. And he also received the prestigious Swarna Jayanti Fellowship of the Department of Science and Technology in the year 2005. He was named the DAESRC, that is Department of Atomic Energy Science Research Council Outstanding Research Investigator in the year 2010. Menon is not only a committed scientist working at the intersection of physics and biology, but is passionate about science communication, science policy, and all the issues that impact our world. Along with a couple of others, Menon became the face and voice of science, talking about COVID-19 during the pandemic. He is a sought-after speaker at various academic meetings and gatherings in India and around the world. Let us now go over to Professor Menon and listen to what he wants to share about the topic of doing interdisciplinary science. Hi Gautam, welcome to InfoFire, the fireside chat series from Information Matters. Thank you so much for agreeing to be part of this series. Welcome.
Thank you, Shalini. Very happy to be part of the series.
Now, the topic of our conversation today, of course, you've been doing this, is doing interdisciplinary science. So you are trained as a physicist and now you are a professor of physics and biology at the Ashoka University. In addition to now, recently you've been appointed as the Dean of Research. So share with our viewers your personal journey of becoming an interdisciplinary scientist.
I started off being trained as a physicist in my PhD training and my master's and my bachelor's before that. And I was interested initially as a younger student in chemistry, not so much in the life sciences, but from there, from chemistry to move to physics, I did that because I felt that physics was, in a sense, a simpler science. What you had to know to understand physics could be written down on a couple of pages, and everything else was built up on top of that. And that was a very inspiring feeling for a young student. So that made me decide to do an undergraduate degree in physics and later a master's in physics and then a PhD in physics. And even there, you have to make a choice as to what area you want to specialize in your PhD. I started off wanting to do fairly esoteric types of physics, and then really realized that what I was interested in is actual contact with experimental data, understanding complex systems in a sense, and how to understand properties of things that were made up of many, many small constituents, like a piece of wood or a metal or something like that, with millions and millions of atoms. How do they combine to give this large macroscopic piece of metal or piece of wood or concrete or whatever, the sort of properties that it had? So that's what I began to do when I began to do physics. And then later I expanded to realize that thinking about complex systems in general was very useful in terms of concepts that I could be applied to many other different areas. So one area was, of course, the field of thinking about physics in biology, which at that time in the late 80s, early 90s, 2000s, etc., was still a relatively new field. It isn't as if people had not thought about it earlier, but somehow the realization that many techniques that people from physics understood well could be applied to this area was, in a sense, beginning to fall on fertile ground. So I made a sort of move from pure physics to thinking about physics in other contexts, in particular in biology, and then to thinking about biophysics. From there, I made another move, which was to think about even more different types of complex systems. In this case, how disease spread within a population of people. That's one of the true problems of complex systems, if you can think about it. It has all the heterogeneity of people, all the varieties of social behavior, of physical context, etc. And then to ask within a particular social context, within a population, how did disease spread, seemed to be really a question that lay absolutely at the frontiers, not just of computer simulations, not just of ideas about complex systems, but also about concrete problems in epidemiology. And of course, that was a point at which I had already begun to think along these lines for a few years. But then, of course, the COVID pandemic took over, and much of my work really shifted to thinking about areas in epidemiology and how to think about models in epidemiology. So you can see the shift in my interests. And overall, the broad base of this is how do you think about systems with many parts, many different complex types of behavior, and how they interact with each other. And that the paradigm for thinking about that can be applied to many different situations. So in a sense, I think I came to thinking about interdisciplinarity from that particular angle, not by starting out in the beginning wanting to be interdisciplinary, but finding that my interests had moved into areas that required interdisciplinarity.
So, in essence, if I have got it right, it's the complex systems or complexity of world around us, in a way, brought you to this interdisciplinary approach to studies or research, right? And that's what essentially has been this the so-called interdisciplinary approach to science has been, which has been a buzzword for the last 100 years or more, because, I mean, science itself moved from solo research to team research, etc., especially post-World War, government involvement in research, etc., led to this. So, I mean, many of these, whether it is the space explorations or the defense studies, and then later, of course, the genomics, all of that have been driven by the complexity of the subject or the problems, and then the government or the big Sam to say, sometimes the governments being involved with it also led to this. So some would also argue that it is all of these that has actually made this interdisciplinary in a way, I'm saying the Z thing, like, okay, everybody's talking about it. So is it really a necessity, as in, some people say today it is imperative, especially post-COVID. They say you cannot solve problems of the world from a single discipline or from a single disciplinary perspective. So what's your take, or how do you argue with the people? It's not just a government or the funding agencies such as NSF or whoever it is, right? And even in India nowadays, any funding proposal, grant proposal, they say you have to have more than one discipline. Or so what is driving it? Is it the need pull or the whole system, I would say?
So I think in some ways it can be carried too far. For example, I don't see why every research proposal has to be interdisciplinary. There is much research that can remain purely within a disciplinary silo, which doesn't really necessarily have to interact with other disciplines because it deepens understanding. It deepens our knowledge in that particular area. But let me give you examples, two examples of areas that I think about where being interdisciplinary is absolutely crucial. One area is the area of climate change, and the other is the area of infectious diseases. When we think about climate change, it's possible to think about climate change from a purely technical or technological or engineering perspective. We can worry about how humidity might change, patterns of weather, large-scale circulation, global climate models, etc., etc. And that would tell you about a bunch of scenarios for how climate might change in the future. And one can get to increasingly refined ways of understanding this by improving the sorts of models that we have now been working on for the last 40 to 50 years. We understand the many different components, the atmosphere, the ocean currents, the incoming sunlight from the sun, how all of these interact with each other. But there are other parts of it that are purely social parts. For that, in order to effect a large-scale change in the nature of our climate, what we need to do is to be able to A, move forward on technological innovation, but B, also curb our own patterns of consumption or change our patterns of consumption. For example, accustom ourselves to driving less, burning up fewer fossil fuels, shifting to more sustainable alternatives in what we do. All of these are moves that involve society, not just the science. And of course, there's an economics of climate science. What are the right incentives that you must bring to bear? There's climate science communication. How do you tell people what to do? What are the right nudges to choose in that? So the whole climate science and health, for example, how is it that we expect human health to change in the background of a changing climate? Now you begin to see the question of climate change is just much, much more subtle than you might preliminarily or initially have thought it to be. It's not just a problem in engineering, it's not just a problem in economics, it's not just a problem in physics or biology or medicine or anything. It's all of these together. And with these problems, there comes something called wicked problems, because you can't change or address one part of it without influencing some other parts. For example, a geoengineering solution to climate change might mess up other parts, for example, ecology of life on Earth, in ways that we have not anticipated yet. So really, to understand and approach these problems, you need at your core to think in an interdisciplinary manner. And even if you belong to one discipline, to be able to talk to people across disciplines, to integrate what they say into a common understanding. My second example is the example of infectious diseases. And here again, the way a disease spreads is not just a question of how a virus moves from a person to person, but in what context do they move? How does society influence the interactions between people? Why do infectious diseases affect some subpopulations much more strongly than other subpopulations? For example, if you're poor, if in the United States, if you're Black, if you belong to disadvantaged caste groups, etc., your chances of falling ill with, say, a COVID-19 infection or any infectious disease are disproportionately more. So how does this combination of social status, economic abilities, etc., all come together to determine your susceptibility, your likelihood that you will fall ill? That's again not just a question of disease, it's not a question of epidemiology. There are many other components that must come together in our understanding. And I think the frontiers now are to understand these many additional parts, not just the biology, which on its own is fascinating. Why is it that some people fall severely ill, some fall mildly ill? What is the nature of the difference of the host behavior that predisposes someone to more severe outcomes versus milder outcomes? That's a separate question altogether. But to understand this in a larger framework, it's impossible to do it without understanding society. And to understand infectious diseases and in populations, all of these subjects must come together, must collaborate together to deepen our understanding.
Let us now get back to the basics, because I would like to have your view on the definition or the defining characteristics of what is interdisciplinarity is, okay? Because, there are so many other words which are used interchangeably, like multidisciplinary, cross-disciplinary, pluridisciplinary, etc., etc. So my question is it about the integration of different perspectives, knowledge, expertise, etc., or is it transcending them in a way, you kind of develop a unified approach?
I think in the beginning, you must integrate and then you must transcend. There's a certain order in which it has to happen. First of all, people from different disciplinary backgrounds must come together to find that common ground, that common area in which they can talk, to develop a common language by which they can interact. From that, hopefully, the science of the future will be much more integrated. And it's important to ensure that the students that we train, this also becomes a part of their training, how to collaborate, how to interact. None of us, I think I still would maintain that you cannot make a person interdisciplinary from the beginning. It's important for them to understand one discipline deeply enough. But then it's necessary to transcend that, to understand where that discipline interacts with other disciplines. And after that, where even that interaction can lead you further from science into society and the interaction between science and society. And that, I think, is probably the last frontier. But one must always start, in my opinion, from a disciplinary base, because that's your home territory. That's where you're really coming from. But the next step beyond that is to understand where your discipline interacts with other disciplines and where it draws from these other disciplines and where it can give to these other disciplines. Once you have a common framework for doing this, then one can move toward the region where everyone else is more comfortable, understands the true connectedness of sciences and the social sciences in a way that enables us to be able to tackle the hardest problem that confront mankind together, climate science being just one of them.
So what you're saying is that first and foremost, you have to have a discipline, whether it is physics or biology or economics or what have you, and then you move towards integrating or at least moving to another discipline or borrowing and having teams. That's what you mean, right? So you have to have first your grounding in a particular discipline. So you become a physicist, you become an economist, and then you move towards other things. Well, that brings us to the question of, for example, when you become a physicist or a biologist or whatever, see, any discipline is defined by the theoretical, the background or the framework of the discipline, the definitions to everything, right? The theory behind it, which many a times within a discipline also keeps changing. To use, the Kuhn's concept of, paradigm, for example, which brings about this revolution, scientific revolution. So within a discipline, sometimes, there could be, what I'm saying is there could be difference of opinion between, let us say, someone who's grounded in the classical physicist model to someone who is, this positivism, relativism, etc. has come, right? So if in such a scenario, how do you really become bring about this integration or transcend when sometimes it is not I would say you cannot combine them, or you cannot, they're too diverse.
So I mean, there is in a sense a distinction between various sciences. I think at the level, just to take the example of either climate science or diseases, we understand the physics at that level very well, and it's unclear that any much deeper understanding of some much smaller scales, where the atoms are, whether electrons are truly made as strings or other, there might be some other unknown subatomic physics that we don't understand yet, whether they influence what we know currently about physics at our scale, the relevant scales to thinking about cells and diseases, that's pretty much out of the picture. We do know everything that goes into our universe at the moment, at the scale that we're interested in, and we can probe. On the other hand, topics such as biology are still at a stage where there's much that we don't understand. We don't understand everything that we really need to know about the human immune system, to take one example of something that really affects how people respond to diseases. So there it's possible for new paradigms to come in, to shift in subtle ways, in ways that in older, more established sciences, it's harder to imagine that this would be so. Certainly, there could be changes in language, in the way we describe it, and maybe one could figure out a more accurate language, for example, to talk about quantum mechanics. But in terms of ideas and concepts, I would think that most of these are in place. We're not seeing large-scale revolutions of the sort that happened when quantum mechanics replaced the earlier Newtonian thinking. And we understood that these were really limits. When we talk about something very small, we have to use quantum mechanics. But in some limit, that must become classical mechanics of the very large, in the larger scale. So, of course, these are purely disciplinary problems. One's own discipline changes, concepts change, ideas change, presentations change. What you assign importance to also changes with time. But I think that's really the reason why you need disciplinary expertise, to understand, as the landscape of your own discipline changes, how does that relationship to other sciences and other disciplines also change? Which again, you summarized what I said very well. I did say, and I do think that to be disciplinarily grounded gives a person a certain confidence and also makes them useful to other people. In order to collaborate, everyone must collaborate on an equal level. The biologist must understand biology, the clinician must understand clinical medicine, the physicist must understand physics, the social scientist must understand social science, and sociologist sociology, because only then can they bring what is absolutely the frontier level of knowledge in their field into a common understanding of a jointly set out problem. That's the way I would think about it.
So anyway, I do agree with you that, you have to have this, and it's not that I'm not agreeing with you. I'm just trying to sometimes, my own experience is that it's, in a sense, I would say these disciplines are like in the Indian context at least, like the caste system. People don't want to, even however much they say. Sometimes, inherently they feel that I am a physicist. I'm not saying you are doing it or I am doing it or XYZ. Generally, I think, I'm a computer scientist, I'm a physicist, etc. So that's one problem. The other one is the way in which the pedagogy or the education happens, right from your undergraduate days. You are saying, yeah, this is physics. You have that, even there is this hierarchy also. Oh, I am a PCM student, not a CBZ student, and all of those things happen. And usually, even at least in my case, the other day I discovered somebody was in the same college, during the same contemporary, but I didn't even know that she existed in my college because she was from CBZ. I am a PCM student. Okay. Anyway, the point I'm trying to say is that there is this, sort of I would say the pedagogy which says, hey, you are a physicist. This is how you think. This is how you develop your perspective, etc. And there is this interdiscipline. So what is the way forward? Is it something like, let me think of, for example, the Bertalanffy's, general system theory approach. That you see commonalities, right? That general system theory approach was primarily about everything is a system. It's a biological system, physical system. So some such conceptual, or I would say foundational thing also has to be taught at a very young age. Young meaning I'm talking about maybe the high school or even undergrad studies, wherein you have to have the double vision. You are a physicist, but then there is this, larger world outside, the nature, whatever, which is a complex system which involves all of it. How do we do that as educators, for example?
Well, that's a wonderful question. And usually, this sort of comes up when I teach a foundation course at Ashoka University. So the foundation courses are a set of 9 courses that have to be that are across, literature, science, social sciences, humanities, etc., etc. And students have to choose some set of these. And among the courses that they can choose from, is a course that I teach called the Principles of Science. And the students in the Principles of Science course come from all sorts of backgrounds. Most of them will not wind up doing science. They will go on to doing economics, or they will go on to do psychology or some other area where science, physics, chemistry, mathematics, etc., is less relevant to what they do. So it's my challenge as a teacher to try and interest them. So some of them, for example, may not have done mathematics or physics, etc., beyond the 9th standard or the 10th standard. Some of them have an active dislike of these subjects. I often find students who say that I hated mathematics, I couldn't understand the word, I did very badly, I'm glad I stopped studying mathematics. And then I have to sort of introduce them to the mathematics that is required for the course that I'm teaching, and try somehow to convince them that this isn't the end of the world. There is something that you may have missed when you studied it for the first time. There's the dislike that you have may not be rooted in true fact. And let me tell you something exciting and remarkable and exceptional about these things. So the last time I taught this course, I usually focus on a different area. The last time was around climate change. So the idea was to look at one report, which is a report prepared by the US National Academy of Sciences and the Royal Society, an update report in 2020 that outlines the science of climate change and what we know about it at a level that is probably, you need some scientific background, but not too much. But it does have some technical terms. It has terms like the greenhouse effect. It has terms like global warming. It has terms like carbon dioxide, parts per million, etc., 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 and a bunch of discussions of the policy issues around that. So we made it our aim to try and understand the document by the end of the course by supplying all of the ingredients that you needed to know about the science that went into this. So that's all I did. I said, this is the problem. This is what we are seeing. This is what we believe will happen. Let's go back and find out how we figured this out. How do we know that the amount of carbon dioxide in the atmosphere is increasing? How do we know what the consequences of that increase might be? What does it mean to have a 1 degree or a 2 degree change in temperature over a period of 5 years? What happens when sea levels rise? Why should sea levels rise in the first place? What happens to how our bodies themselves cope with an elevation in temperature? What are extreme events in climate? What happens with vector-borne diseases? For example, we know that the mosquitoes that carry malaria or dengue, etc., are all typically confined to a certain range around the equator because they find it hard to survive and reproduce in colder climates. But as the world overall gets warmer, you can expect the range over which you find these mosquitoes to expand. What are the consequences of that in terms of the additional numbers of people who will now be susceptible to disease? What about waterborne disease with extreme events, for example, like the floods in Pakistan? What happens in that particular situation? How do we piece this information together? And they suddenly begin to realize this is not a physics question, it's not a biology question, it's not a social science question, all of these together. So it's that feeling that I would like, these are people who've thought of these problems for the first time. And it's probably easiest to teach it at that level of the first year undergraduate course where they're still excited about what they're going to do. They haven't quite made their decisions yet about what they want to do in the future. But you can really excite them with ideas at that particular point and encourage them to think freely. And then at that point, they suddenly realize that, look, to really think, this is not a problem in economics. This is not a problem in engineering. It's a problem in all of these things together. And science is but one tool. Science, mathematics, all of these are different ways of looking at the same problem, but all of them must be integrated together. So I do think, investigations like these into what makes for effective teaching of the need for interdisciplinarity is important. I'm still very open to thinking about how to do this at the school level. I think it's important to introduce these ideas there, or at least at the early college level, what might be good pedagogical techniques for doing this. And I think that's going to be a question in the future increasingly. How do we teach students to suddenly encounter this range of different problems, these truly wicked and difficult problems, and to understand that a unidimensional approach to them will not work, will only be a partial answer.
Yeah, I guess, and I would agree with you that it should start at the school level, and probably we don't even have to say this is physics, this is biology. We said this is probably science, and science in a very broad sense, including social sciences and human sciences. This is society and science. That's it. In a way, you look at how you do it. Well, that brings us to my next question. How are we going to teach? That is the pedagogy. From curriculum to teaching methods. Whether it is active learning. All of those experiential learning methods, etc. How do you instill this kind of a interdisciplinary habits of mind? Are there any, have you thought through or have you been sort of practicing that kind of a different, I would say, teaching techniques and style, etc., in your courses?
So in a sense, that's what I tried to do with this course. When I discussed the uncertainties in, for example, measurements of the amount of carbon dioxide or predictions for 20 years from now, where will the temperature be under different scenarios. I then introduced the idea of uncertainty, then from there, probability, how to think about probability, different consequences of probability, of probabilistic thinking, of Bayesian approaches to thinking about probability. And suddenly that discussion expands a little bit. What I did was to motivate discussions of statistics, of mathematics, of physics, of chemistry, etc., starting from this broader question. And I find that usually works better with students at this level, especially students who are not sure they will be interested in the material at all. Climate change is something that everyone can relate to because they all feel that they can see it in their own lives and what their stories, their parents and grandparents have told them, and what they read in the newspaper, etc. But to prick their curiosity, to sort of push that a little further and to say that, look, in order to really understand this, look at all of the different fields that must come into play. That's the angle that I take. I find that works well, in the sense that many students who initially came to me and said that, look, we don't like mathematics, there's too much science in this, etc., etc. By the end of the course, a number of them have converted to saying that, look, I now see why this is important. I now realize what I missed in school in terms of this understanding. So maybe this is one way of teaching science, that you start with a broader problem with aspects of society in it so that they can intuitively understand it. It's not just, why is the sun, why is the earth moving around the sun, what happens if a ball hits another, etc., which are all sorts of abstract problems that, that can be studied easily, but don't really evoke a visceral reaction or emotional reaction in you. But if you start from these larger problems, it's easier to make people understand where science comes in and why it's important, and why these results that we have, how much we can trust them, how much we should not trust them, and where society and science must talk to each other.
That's nice. So what's been your experience? You think that you've been successful in getting your students to think in an interdisciplinary manner and still, have the depth and grounding in a particular discipline? What's been your experience?
So I think that the real depth and grounding will come in later. But I think overall with the class, of course, you'll never know with a large class of 150 students, you certainly are not going to reach all of them. But at least the few of them, who was initially against this whole idea of why am I doing a principles of science course if I want to do sociology or anthropology when none of this is relevant, have been converted to the idea that you do think that understanding different parts of science is fun. Is A, fun, B, useful, C, vital to addressing these larger questions. If I manage to do that with even 10% of the class, I would be very happy. And I think that's probably the right level to think about of actually reaching.
I think those 3 points are really excellent, that it is fun, and then it is important or vital, and then thirdly, the purposeful, it's useful to society. That's how you do it. I think if we can instill that in children, students, etc., that would be great, because learning and researching or any of these things should be fun. Number one, that's important, because
exactly.
if you enjoy it, only then you will like it, and then all of that comes in, right? It's fun, and then it's important, it's vital to the society. And you cannot be any kind of a student, according to me, without at least having some basic thing about maths or physics or sociology or whatever, right? So that's vital. And third one is that it is useful, it's fruitful. And that's how even the smallest change that you're going to make in this world is going to stem from that, or at least it's going to be stemmed. I think that's a very important point. I think you need to get this into a kind of a capsule, right? For the students to say, well, you go ahead and become a sociologist, or you go ahead and become a mathematician, but you also have to have this perspective. That's good. So basically, that also leads me to the next question, because once they have this in their, mindset, or what they call as the habits or culture, all of these things, if you use the Kunst, all of these things are almost same as paradigm, right? The culture of doing things, the mindset, the habits. So it also leads to another important aspect of today's modern science, as we say, our science, the republic of science, so to say, is collaboration. It also makes it easier to collaborate, and makes it, collaboration as an imperative. But again, let me also become a devil's advocate again and say there are people who say, hey, this collaboration, etc., is also a kind of, pushed by all these funding agencies. And also, another aspect is people are now saying that, I'm sure you're aware of this, what they call as the hyper authorship. There are papers with more than 1,000 authors. That has been increasing, especially in some disciplines, including your own discipline of, when I say your own discipline, I mean this genomic research, epidemiology, and all of this. There's been a surge in the hyper authorship. And some people view that as a method or a strategy to gain the scientific enterprise of measuring or evaluating scientists in terms of their productivity, in terms of their impact factor, right? So you have multiple authors, hundreds of authors, then all of them get some kind of credit for each of these papers. Do you see any connection, or is there some validity in that kind of a criticism, or even I would say, blame that is put on this hyper-authorship, which is a result of all this multidisciplinary.
So let me sort of address that in parts. One is a question of the sociology of science itself, and the way we have approached our changing approaches to authorship have altered across the past few centuries. It wasn't uncommon even about 50, 60 years ago for assistants to do much of the calculations that went into the paper. Or sometimes, often these were female assistants. Often they contributed very importantly to the substance of the paper. But when the paper was finally published, only the name of the senior male author would ever appear onto that. We now recognize that this was wrong, that if you contribute at a fundamental level to developing a certain advance, then your name, you should be credited for that. You should not be forgotten and consigned to the dustbin of history. So that certainly has changed. The fact that people who contribute to any work must be part of that, part of the authors of that work, and not just either just thanked in an acknowledgement or not mentioned at all. However, it's possible to carry that far in a far more extreme direction. People who barely have any contact with the experiment that was done, the discussion that was going on, etc., will now demand to be as part of the paper, or even if they don't demand to be, one feels a sense of, some authors, some senior authors feel a sense of obligation to them. For example, if you have undergraduates working on a project, even though their contributions may not be as signal or significant as the postdocs or the PhD students who went into that. Nevertheless, this is an exposure for them for the first time to research, and to enthuse them, it might be felt necessary to add them onto the paper, even though their contributions may not have been as significant as to warrant as unique authorship. The lines to draw here are often very difficult, and it's not very clear that there is a universal answer to this. Every investigator comes up with their own solutions to this particular issue. That's one thing. It's certainly possible to carry it too far, where you have minor contributions that really should not be part of that. But it's also true that science is now inevitably a collaborative thing. That a big experiment, for example, like the Large Hadron Collider experiment at CERN, this requires many people to come. People who design magnets, people who design low temperature cooling systems, the theoretical people who model the collisions between particles, people who work on what is called phenomenology, of looking at particle tracks and understanding, was there a new particle that was created in a particular collision at a particular energy? All of these people contribute together to that understanding, and you cannot remove any one of them away from this and hope to have achieved that same understanding. So whether you like it or not, whether in large-scale genome sequencing projects, whether in large-scale particle physics projects or plasma fusion projects, etc., the reality of the world is that many people must contribute. This is certainly very different from the way science was done 50 or 100 years ago, where one single individual, or maybe one or two working together, could hope to make very signal discoveries at that point. Science is no longer at that stage. It really has changed qualitatively. And I think increasingly awards like the Nobel Prizes must recognize that there is no longer a single individual who does things, but often a group, and you cannot subtract the contributions of any member of that group without affecting the contribution itself. So I think it's important to convey to students the necessity for collaboration and the importance for collaboration and the rules for collaboration. They must all learn how to be successful collaborators in a particular enterprise. This is a skill that's not just valid for science, not just useful for science, but even outside science. And so that's something we should, in fact, it's good that you stress that. The need for collaboration, the importance of collaboration, and the understanding of how to collaborate effectively is something we don't teach our students yet, but it's certainly part of their toolkit for the future.
Yeah, that brings me to another question. I mean, collaboration is great, etc. But again, I mean, it's not about interdisciplinarity or different disciplines. Even, I mean, like sometimes I find it little hard to come up with a paper without having to get into all this with my, I mean, student or co-author, right? Because her view is, I mean, recently, in fact, talking about it, I mean, one of my areas of research is scientometrics and infometrics. So we are trying to write a paper. I mean, we have done some studies about how the COVID research from India is, what's the collaboration that is happening, patterns, collaboration patterns, etc. Somehow we have not been able to arrive at a consensus regarding even what should be the approach, whether it should be the metrics or it should be this. What I'm trying to tell you is, it's nice to have collaboration. Yes, she does certain analysis, I do something else and all. I bring too many, I mean, even between two people. We bring different, I would say, strengths to the table, right? But at the same time, sometimes, getting two people to agree on a particular thing itself is kind of difficult. So how do you achieve that? How have you done your experience?
So I collaborate with many people. I collaborate with many experimentalists across the country. I've done so in the past. I'm part of multiple collaborations where I've authored lists with about 10 or 12 people, with large experimental groups in physics earlier. I've also done that. You must be committed to collaboration. I think that's important, that you must say that, look, I cannot do this on my own. I need your help, and I need your help in these specific areas, and I need your help in these specific areas. And here's the problem that we want to set out to solve. So once that is clearer, it's not clear that there's no one person at the top dictating downwards what should be done, but it's more a question of how do we solve this problem together. That your attitude shifts a little bit and changes in an important way. And that, I think, is the important thing to actually convey. There's no secret sauce for good collaborations. Everyone figures out their own way of dealing with it. Some people are just better collaborators, some are worse. You begin to figure out who to avoid in a collaboration and who makes the collaboration succeed. And the best collaborations are where every individual realizes what they have that's unique to contribute, feels a sense of excitement about contributing that, and seeing the whole emerge as a combination of many different parts that you put together. I think it's important. It also makes for better science to understand that what is important to the problem. It's not you. It's important to understand what is the problem that has to be solved and how many people can contribute, and should contribute to that understanding, which would be imperfect and incomplete without all of their individual contributions. I think collaborations, as we said earlier, are going to be central to the world going forward. And it's important for us to teach students the soft skills involved in collaborations and the mechanics of collaborating early on.
I think I totally agree with you. We need to have probably a short course in our academia about collaboration, the need, the methods, and the attitudes that you need to have, the styles, and all of that needs to be taught, because we think that as we know, over the decades, at least in my vintage, I can say so much has changed from what we were doing some 40 years to now what we are doing. So we need to adapt to these changes when it comes to teaching the future generation of students or researchers, that all of this is going to be important. It's not about just doing science or doing research. It's also about how you do that research, not just research methods again. It's about collaboration. I think it's important. Maybe you should come up with a small module or a course on collaboration itself. Right? So that brings me to another final question, which is very specific to one of the, a so-called new interdisciplinary disciplines, that is, quantum information science. Okay, since you have been working in quantum and I have been in information science, I thought let's hear from you. What's about this quantum information science and how is it going to change the future?
So quantum mechanics has introduced a bunch of very unusual ideas into the way we normally think about how we describe physical systems. We understand that what is fundamental is the quantum state of a system, that there are what are called probability amplitudes for the system to be in any number of states that it can possibly occupy. And these probabilities come from these probability amplitudes in a particular way. So quantum probability is a somewhat different animal from classical probability, from the normal ways we use to think about probability of a coin being tossed or a dice being thrown. You can have multiple possibilities that coexist, multiple possibilities at the same time. And the very act of measurement crystallizes one of those possibilities. These are the things that one thinks about when one thinks about quantum mechanics, quantum probability, and the implications for how information is transferred using quantum mechanical means from one point to the other. What we understand from the early work of Einstein, Podolsky, Rosen, and other people who came after that is the sort of strange quantum mechanical constraints that operate, by which you can have two particles that are entangled. The technical term is entangled together, but then can be separated very far away. And then making a measurement on one particle will automatically tell you about something about the other particle. So this looks nominally as though it's a way to transmit information, to control the flow of information across very large distances. And of course, one has to understand the sort of physics behind that, especially in the context of what we know about relativity and the finite limits on how information can actually proceed from point A to point B, because we know that the speed of light itself sets a limit on how fast you can move a signal across a particular distance. Quantum information theory and its cousin, quantum computing, which uses the same sets of quantum mechanical ideas, are, I think, very important elements of what might be potentially in the future ways of designing equipment, designing new computers, for example, that can do things that classical computers cannot do. That's one, or at least to do things much faster and in unimaginable ways classical computers could not do. Where quantum information theory comes in is probably a little more subtle, and that has to do with old work by Shannon who defined the foundations of information theory in terms of probabilities associated with certain signals and the information content in those signals. Now, the way we understand information in quantum mechanical context is in a sense deeper, broader, and more significant than we understand it in classical context. And it's these ideas that, in a sense, are still developing. We still have to understand where we can go with them. But the interplay of quantum information theory and quantum computing, I think, will really be important in the coming years. We're not very sure how important. Can we really design new computers that use these principles? Or is it just, are we just going to be overwhelmed by the fact that you have to cool things down normally to very low temperatures to make them function quantum mechanically? And so a room temperature quantum computer may be something that's not possible at all. But the other questions that I find very interesting is, does quantum mechanics enter biology? Are there parts of biological systems that are inherently quantum mechanical, that use quantum mechanical rules? Is information encoded in biology using quantum mechanics? We have very, very little idea of this. There have been lots of speculation and some very preliminary results about this. But I view that again as the real frontier of science for the future.
I mean, since you brought the topic of information theory, etc., let me also ask a general question about theory. In fact, one of the, I mean, this is actually fairly, at least 15-year-old, I think, this statement, because of the emergence of, big data, data itself, scientific data, etc., that it is the end of theory because the data is going to actually show you the patterns and you come up with that. What's your view on that? Is it the end of theory because we are going to, I mean, all the theories are going to emerge from the data, right? Are the patterns that we see in the data?
That's a wonderful question. There's no doubt that you can extract patterns from data that in many ways you might not have anticipated. Is it possible to think of a computer that might have come up, for example, with the idea of with the deepest idea, the quark model for subatomic particles such as the proton and the neutron, or the idea of string theory, or the idea of general relativity? Could it have come out just from nowhere? And I would think it would be very hard to do. I mean, what you input into a computer, finally, what you provide to the computer as a starting point, the data that you provide as a starting point, implies a certain effort at collecting a certain thing. You're already predisposing the machine to give you answers that depend upon what data you have supplied to the machine. You may think that, look, I've been completely agnostic about the data that I've supplied to the machine, but in practice, that is never true. So I still think there is an important role for human thought, for human analysis, for geniuses like Einstein and Fermi and other people like that, to come up with completely different ways of synthesizing information and really making you think in ways that you have never thought before about physical ideas. I don't think the machines are there yet. They still have a lot. I think they can still surprise us with some things, but there are things that they will just not be able to do, in my opinion.
Yeah, talking about missions, have you tried the talk of the town, the GPT, the chat?
I haven't tried it yet, but I keep seeing lots of examples of very clever things that it has done. And I quite understand the concerns of many people in the humanities and social sciences that, how would you tell an essay written by GPT chat from an essay that a real student would take? And often, on the face of it, many of them look very convincing. And I have no doubt they will just get better with time. Can they do the same thing with equations and computer programs? Some computer programs, yes. I haven't seen, for example, a derivation of a complicated result from fluid mechanics or something coming out of GPT chat. Maybe it can do that. I think the primary problem will be pedagogical. How do we tell whether our students have faked their answers or not? Have they just submitted this question to GPT chat and taken the answers out? That will be a challenge for us to figure out how to make that distinction. And maybe we just have to adjust our pedagogy accordingly. So ask the sort of question that cannot be answered using a mechanical tool such as that. We have to see how best to do that. We have to change that completely, our teaching methods.
Okay. Thank you so much, Gautam, for your time and your energy in doing all this. Thanks for joining us. We will reconnect once again. Hope to see you in person sometime, somewhere soon.
Yes, Shali. Thank you so much. Thank you for a wonderful conversation. I really enjoyed it. Good luck and good night.